So, we come back to this particular slide. I hope you have tried to draw the plots, the cumulative plots. So, now let me reveal how would the cumulative plot look like. First one is very easy, it is a simple sigmoidal curve. Now, when you have a very broad distribution, as you see in this particular case, this line, this cumulative plot also becomes very wide, or the slope becomes very small. On the other hand, when your distribution is very narrow, like in this particular case, which is also called monodispersed distribution, then this becomes more like a step function. Most of the data would lie within this. So, it starts from 0 and reaches 100% very soon, and this is how the cumulative plot would look like when you have a bimodal distribution. So, you have one mode here, another mode over here. So, here in terms of cumulative plot, what you see is a step saturation, and then again it starts to increase beyond a certain point. So, these are the different kinds of cumulative plot that you can obtain. However, like I said, log normal is the most common when you have particle size from one particular method. Let us say you mix particles from two different methods, or obtained under two different conditions. In that case, you may as well get a bimodal distribution, and so on. Now, coming to the different kinds of plot. So, this is your simple linear plot. So, here this is how the distribution looks like. As you can see, it is right skewed. This is how the log normal distribution looks like. This is how a cumulative plot looks like, which we have been discussing so far. And the last one is very interesting. Here what we are trying to define is on the y axis standard deviation, and on the x axis log normal distribution. Now, you remember, for each and every diameter we have, you can say there is a D50, D10, D90. So, for each and every standard deviation, you can say there is a corresponding diameter which represents how much fraction of data lies over there. For example, if you go to the 0 standard deviation, which will be somewhere over here, this will be D50. Now, if you go to +1 standard deviation and -1 standard deviation, then over here it will be D50 plus 32. So on, it will be D82, and here it will be D50 minus 32, like D18. So, D18 to D82. So, this is how you can always draw a corresponding diameter which represents how much fraction of data lies below this, and draw against it number of standard deviations. Now, this is a very useful plot, because whenever you have a normal distribution, or in this particular case log normal distribution, you will always get a plot like this. So, here what is it representing? Fraction of data, or equivalent, or you can say equivalent to that, what is the equivalent diameter. So, for 100% data you will get a D100, for 50% data you get D50, D50 is where you have the mean value, and for 20% data you get D20. And just to bring back in our memory that we are talking about log diameter. So, this is not really D20, but log D20, this is log D40, log D60, and so on. Now, the interesting aspect about this curve is that it is very linear, somewhere from 10 to 90. So, 10% to 90% data, when it is plotted against the standard deviation, it comes out as a standard, or it comes out as a linear line, it is a straight line. Now, if you know this fact, and this will be true whenever you have a normal, or in this particular case log normal distribution, we can use a relation like this. So, now what we are saying is that, so this is the mean, so this is D50, so this is corresponding to D50, actually log D50 to be precise, and like I said, somewhere over here you have 90% data. So, this was 50% data for that matter, and therefore, corresponding to that you have log D90, and somewhere over here you have 10% data, therefore, corresponding to that you have a diameter D10, log D10, and in between these, so over here you have, we can call it standard deviation 0, somewhere over here you have -1, somewhere over here you have +1. So, in between these standard deviation you have, remember, 68.27% data, and somewhere over here you have -2 and +2. So, although this is not linear, but we still know that within this plus minus 2 sigma you have 95.45% data. Now, if we look at this value to this value, and let me draw it with a different chalk, which is a straight line. So, for this particular line we can also find corresponding what is the sigma value. So, there is a minus let us say z, and over here a plus z, and it is very easy to show that this z is equal to 1.28. So, if you take ERF 1.28 by root 2, what you get is 0.8, meaning 80% of data will lie within this, from here to here. So, let me again emphasize this. If you are looking about, so this will contain, this diameter to this diameter will contain 80% of the data. We know this from the corresponding standard deviation, which comes out to be 1.28. And if we have to look at the slope of this line, this slope can be defined as, this is plus 1.28, this is minus 1.28. So, this minus this will be 2 times 1.28, which is 2.56, and on the x axis we have log d90 minus log d10. So, we can write it as now this is true for no matter what the distribution is, because we have not yet put any actual value. We have just put symbolic numbers. D90 represents some value where 90% of the data is. D10 represents is a symbolic character which represents the diameter below which 10% of the data lie. So, once you put this, you will be able to get a slope of this line. Now, when this slope is very large, what does it imply? It will imply narrow distribution, meaning this line becomes very vertical. Then the we have narrow distribution, something like monodispersion distribution. When slope is small, meaning it goes like this, remember it will still cross 10 and 90 at the similar values. So, by getting this value of SW, you will be able to find what is or what kind of distribution you have, narrow distribution and wide distribution, and at the same time you have another factor, another number, which is mu, which is the average size, average diameter. So, using these two numbers, you have complete information about the distribution of the particle size. So, you see statistics comes to our help here, and we are able to deal with such a large number, something between 10 to the power 9 to 10 to the power 21 particles per kg. That kind of number can be dealt with the help of statistics, and we are now reduced it the overall distribution information to just two parameters, mu and SW. Of course, you can also say mu and standard deviation, but then standard deviation in itself you will have to again manipulate a lot to get a better understanding. Much more suitable number is SW and mu. So, we are able to have a complete understanding of this distribution using these two numbers. So, now we have understood in great detail about the size distribution. It is time that we looked at experimental techniques. So far it was theoretical, now we have the theory to understand the distribution, etc. It is time to look at some of the actual experimental techniques that are used to characterize powder particles. Two of the most commonly used techniques are listed here: microscopy and screening. So, what do we do in microscopy? We use optical, SEM, TM or even AFM micrographs, and we then look at the picture and then try to obtain the area, projected area, and from there you will determine what is the D equivalent. You remember, when we have a projected area, from there we were able to calculate, or we were able to obtain equivalent diameter. So, we can obtain that. So, you can understand the projected area diameter will be the most suitable value when we are looking at images. And in fact, nowadays you even have automated software available to recognize particles and then calculate the area, and then it will automatically give you a equivalent diameter. So, these things have become very easy, and one of the very common image software that is available for free is this ImageJ. It is at this website. Just type for ImageJ at NIH and you will be able to get a link. It is a very dependable software to understand and to analyze the particle size. Second method is screening. It is, you can say, the brute force method. You have sieves of different sizes where the largest particles are made to stay on the top, and the smaller particles are allowed to sieve or permeate through the sieves. And then again you will have another layer of sieve which will allow even smaller particles, and then third layer and fourth layer and so on. So, you will have different sieves carrying a range of particle size. Range will depend from the maximum, the minimum of the upper one to the maximum of the lower one. So, that way you will have what we have been plotting as a frequency or a histogram distribution. So, each of these sieve will become one histogram. Now, these are usually used for particle size greater than 38 micrometer. You will not be able to use it for very small particle size. Considerable propensity of error. Now, here when we are doing sieving, there is a good chance of errors seeping into your data, and that is because in here what you do is you take a sieve and you shake it, keep shaking it until you are convinced that all the smaller particles have permeated through into the lower side. But of course, this may not be 100% way. There may be a lot of fraction of smaller particles still remaining on the top of that sieve, and it will, of course, as you can understand, that it will also depend on the amount of sieving time. If you do it for very long time, you would get lot more smaller particles to go down. If you do it for very small time, a lot of small particles will remain on the top. And other problems are overloading of powders. So, for example, you cannot put too much powder onto one sieve and so on. So, these are some of the problems associated with sieving technique or the screening technique. Here is much more you can say a figure to explain what we talked about, the imaging technique. So, here is an image with particles over here. Now, this software, as you can see, which is the ImageJ software, and here is also the link where you can download it. So, you can see that it can recognize different particles and then convert it to grayscale, and then it will be able to say the area and hence the size of these particles. So, this is the imaging technique, and on the bottom left what is shown is the sieving technique. So, you see you put some say 100 gram of the powder over here, and then you have sieves of different sizes. So, that increasing mesh is the size of the or the density of the wires in that sieve. So, the density of the wires is increasing, which means smaller and smaller holes are available, and the particles flow through to the smaller and smaller size, and therefore, this is the schematic distribution. You will have larger particles over here, smaller and even smaller particles going to the bottom side. Now, that we are talking about the mesh, so let me just give you a quick example. When we say 200 mesh size, what does it mean? We said that when you increase the mesh size, there are smaller particles going down. Now, when you say 200 mesh size, what it means is 200 wires per inch. So, if you have higher number of wires are available per unit inch. It means the spacing is approximately 127 micrometer between each wire when we are using 200 wires, 200 mesh size. But then wires itself have some diameter, and for example, let us say wires have dia equal to 52 microns. Therefore, the gap or the opening is equal to 127 minus 52. Which will be equal to 75 micrometer. So, when you are using a mesh of size 200, particles less than this size, which is 75 micrometer, will go down, will go to the bottom sieve, and particles greater than 75 micrometers will remain onto this sieve. And then you can increase the mesh size. So, over there the gap would be smaller, let us say 50 micron. So, in that particular sieve you will have 75 to 50 micron particle size, and particle size less than 50 micron will go to the bottom sieve. So, that is the way to characterize the powder. Now, you will have a full histogram for each of these sieves. So, each will represent one histogram bar. So, next we look at even another technique for characterization of powder, and this is a very well known technique which is widely used for characterizing powder particularly in the labs, and this is called sedimentation technique. So, what you do is put your powders through a liquid and allow the powders to move through it. Now, this is based on what is called as Stokes law, which says that in a viscous liquid the particles moving through it will reach a terminal velocity. And why does it reach a terminal velocity? Because there are different forces acting onto it. So, let us say this is a particle of diameter d. Since it is inside a fluid, so there is a buoyant force acting on it, which can be given by and corresponding to the weight or the mass there will be a gravitational force which will be similar, except that here we had rho f. Okay, I will define it in a moment, but let me write down the equation first. Here you will have rho m. So, you can see now what is this pi d cube by 6 is the volume, rho f is the density of the fluid. So, it is the amount of liquid that has been displaced. So, this is the total mass total weight of this fluid which has been displaced, and this represents the total mass or total weight of the material. So, this is rho m is density of material that we are looking at. So, it could have been metal, it could have been ceramic or anything but particles, and this is density of fluid that we are looking at. Now, according to Stokes law, these two when there is the particle has been allowed to settle in a liquid, in a fluid, then this particle will start to accelerate to the bottom of through the liquid, it will start to accelerate, and then the viscous drag will start to increase, and this viscous drag will cause the speed of this moving particle to reduce, and eventually a steady state or a terminal velocity will be reached, and at that particular terminal velocity the viscous drag would be given by, so this is the viscous drag. So, this is also in the upward direction. Here d represents the diameter, v is the terminal velocity, eta is the viscosity. So, it is because of the viscosity of the material that this drag is getting generated. Now, when a terminal velocity has reached, therefore, no net force is acting on the particle, and therefore, we can write so the two upward forces are balancing the gravitational forces, and from here you can very clearly see so you will be able to obtain a relation for terminal velocity which will be given by this. So, the particle is moving inside this fluid at a terminal velocity and a uniform velocity, and this velocity is now not changing. Now, if you know the velocity of a particle and if you have put this material or these particles in a glass jar of length h, and if it takes time t to reach, then this Vt can also be written as Vh over t, where h is the length that it is crossing and t is the time it takes to reach the bottom. Therefore, using this Stokes law, we will be able to relate time it takes to the diameter or the particle size. And from here, let me write down the equivalent diameter. So, you can see we have been able to relate d with t. H is a constant, eta is a constant, g is constant, rho m and rho f are constant. So, for if you know the time, you will be able to calculate d, and there are very simple techniques. You do not need to calculate the time for each and every particle. In fact, you can put a weighing machine, and then since you know the diameter for a particular time, you will be able to calculate the weight gain or the cumulative weight as a function of time, and then from there you can calculate the number fraction that is reaching the weighing machine in that particular time. So, there are simpler ways to get this, but the overall idea is that you can use sedimentation as a technique to characterize powder, and particularly powder size. So, you can also characterize it on the basis of size as well as weight. Now, for particle size below 1 micrometer, turbulence from thermal gradients and even Brownian motion tend to make the technique unreliable. So, there are some limitations for this technique, and particularly it is because of the turbulence and Brownian motion, and in fact, this 1 micrometer size is still too small. You would not be able to use it even for something like we have said earlier, something like 10 or 15 microns, because this is for the smaller size. On the other side, we have the upper end, basically the larger size. You will not be able to use it for very large particle size. When the particle size becomes very large, what happens is that the Reynolds number starts to influence the overall settling of the particles. Here, so far we have been assuming that it is the viscosity which determines the settling and it is quick, but if the particle size is very large, there will be two things happening. It will take longer time to reach the settling velocity, which is the terminal velocity, and second, there will be turbulence because of the increase in the Reynolds number, and therefore, this particular relation will not be valid. And in fact, we will solve one example problem based on this to show that there is a upper limit to the particle size. So, there is both a lower limit and upper limit to the particle size that can be measured using this technique. Internal porosity may also exist in the particles, and that may cause a higher drag, which we have not taken into account. So far, when we took a diameter, we assumed that it was solid material inside it, but it may be possible that inside the particle or inside the powder there may be some porosity, and because of which the density, overall density is lesser than what we have been taking it to be. And the last one, the last limitation we have already mentioned, that large particles take time to reach terminal velocity and hence can be source of error. So, the idea is that there will be techniques and there will be limitations, and so far we have looked at imaging technique, we have looked at the sieving technique, and this is the sedimentation technique. Now, similarly, there are some more sophisticated techniques. One of them is what is described here. It is a light scattering and diffraction technique. So, here is a cell into which you allow the particle to move or feed the particle along with some fluid. Now, depending on the particle size and particle morphology, there will be different amount of scattering, and that scattering is captured by a photodiode array over here and some more side detectors that you see over here, and these information are fed into the computer, and then you would be able to depending on the angle of scattering, you would be able to estimate the particle size that is coming through, and with time you will be able to generate data for large statistics, for large number of particles, and therefore you will have good statistics for it. So, depending on the size of the particle, different scattering signatures are created which are recorded using a detector. Limitations are that particle size should be at least twice the wavelength. Now, here we are talking about scattering. So, and this scattering is taking place because of the light that is falling onto the particles. Now, if the particle size are much smaller than the twice the wavelength, then what will happen is that there may be some diffraction phenomena that may start to take place. So, what you want is that the particle size should be at least twice the wavelength. So, although the wavelength will be a very small quantity or something of the order of nanometer. So, we are able to get or we are able to characterize particles to a much smaller length than we were able to characterize using other techniques that we saw so far, like the sieving technique or the sedimentation technique. But even here there is a lower limit, and that lower limit is determined by what is the wavelength of the particles. This method can give a precision of 0.6%. So, now let us look at quickly some one more technique which is commonly used for determining the particle size, and this one is X-ray technique. Now, in X-ray it is well known that when you are trying to do diffraction, when you bombard the particles or the material with X-ray, then the material diffracts and you get somewhere a peak maxima because of constructive interference, and at that particular point you have the relation n lambda equal to 2d sin theta. But at other places what is happening is that there is destructive interference taking place, and when you have a bulk which is much larger in size, then the destructive interference at the other points is is complete. So, for example, let us say this is the theta angle where diffraction should take place. So, if your bulk size is very large, then the diffraction will take place only at this place, and at other places complete destructive interference will take place, and you will see a very sharp line over here. However, when the particle size or the grain size we are talking about are very small, then the complete destructive interference is not possible, and some amount of remnant peaks or remnant interference, remnant constructive interference takes place. So, and that is what leads to these tails over here. So, ideally you would have seen a peak only at that particular theta, this particular theta, but because the particle size is limited, you see some amount of peak or some amount of intensity at angle less than this theta, and also at some angle higher than this theta, and overall you get what is called as broadening, and this broadening can be related to the particle size, and there are very simple relation, one of which is called the Scherrer relation, to find the crystal or the particle size, and you can estimate very accurately the average particle size, although you will not be able to get a distribution out of it, but you can get a average particle size that is possible. So, we will end at this particular slide, but there are some more simple methods, one of which is listed below, and we will go through some of these methods before we move ahead to discuss what are the techniques to characterize powder. So, see you in the next lecture.